Hello everyone. So welcome to the session two of the DSA Code Along series. So in this series, basically we are solving the Geeks for Geeks beginner sheet and going through each of these problems. So today, as is given in the thumbnail, we will be solving eight problems. So starting with Pythonic point, then we'll be moving to coin change problem, BFS, DFS, insert node in BSD, rotate the matrix by 90 degrees, then a problem called sum matrix, and finally we'll be looking at Dijkstra's algorithm. So there are three very essential algorithms in today's session. One is the BFS, that is breadth first search, DFS, depth first search, and finally Dijkstra's algorithm. So all three are very crucial algorithms in computer science, and according to me, they can be used in solving almost any graph problem, or many of the graph problems revolve around the understanding of these problems. So that's breadth first search, depth first search, and Dijkstra's algorithm. So let's quickly get started with the first problem for today. That is known as the Pythonic point. Okay, so if you remember, whenever we find a problem, our approach will always remain the same. So the first thing that we do is read the question properly. Given an array of n elements that is first strictly increasing and then maybe strictly decreasing, find the maximum element in the array. Note, if the array is increasing, then just print the last element, which will be the maximum value. Okay, so what do they mean? So there is this list that first increases in value and then may decrease or may remain the same or may remain the same and start decreasing. So just to draw that out, first let's also look at the input when we have not understood the question fully by just reading it. We look at the input. So they say 1, 15, 25, 45, 42, 21, 17, 12, and 11. So let's just look at the output they're expecting, right? So 45. So basically, this list increases till the number 45 and then slowly starts dropping off, right? So that is what we're trying to find. At which element the array peaks and then slowly starts dropping off or plateaus and then drops off, right? So that is what we're trying to solve. Again, 1, 45, 47, 50, and 5, right? So this here we'll be printing out 50. Now let me just draw this list for you and maybe you'll get a better understanding. So let me have this array like this, right? 1, 2, 3, 4, and 1. So basically what this is something like 1, 2, 3, 4, and 1. So if you look at this list, basically, what we're trying to find is this point. This is known as our Bytonic point, right? The point at which the list peaks and then drops off. A Bytonic point may even be like this, right? 1, 2, 2, and 1. So this is something like this: 1, 2, 2, and 1. So either of these twos can be our Bytonic point. So basically, just to give you some intuition about this problem, so let me just write 1, 2, 3, 4 and 2 and 1, right? So we are going to use, I mean, the basic standard approach would be just something like return max of ARR. So let me just compile this and show you. Yeah, that compiles and let me just submit it as well. Right, so perfect. This definitely works, right? But why should we even try to seek a better approach, right? So let me just show you an example. So the expected time complexity for this problem is O of log n, right? So usually what the max function does is it looks through all these elements and then tries to get the uh, maximum of the array. That's not what we want because we already have these clues about our list that it looks something like a mountain or it something looks like a mountain and plateaus on the top and goes down. It almost resembles a sorted list, right? So we are going to use an approach that is very, very similar to a binary search approach to find the Bytonic point. For example, let us take this array and let me consider this element as L and this element as U. So L is like least index and U is the highest possible index. So we have 1, 2, 3, 4, 2, 1, right? Okay, so just for simplicity's sake, what I'll do is I'll remove this. So U is this 2. So we have the number of elements in this array is 1, 2, 3, 4, and 2. So the midpoint of this list would be this element, right? So 1, 2, 3, 4, 2. So now basically, how do I know if 3 is the Bytonic peak or not? For 3 to be the Bytonic peak, it has to be greater than both the elements adjacent to it, right? In this case, 3 is greater than the element before it, but 3 is not greater than the element after it. So what basic intuition this gives is that 3 lies on the left side of our Bytonic peak, right? So as you can see, 3 lies on the left side. Now let's just take a look at this 2, right? 2 is, if no element exists, or let's say even 1 exists, 2 is less than 4, that is the element before it, but 2 is greater than the element after it. So what does this mean? That 2 lies on the right side of the Bytonic peak. But only this element, 4, if you look at it, it is both greater than the element at the left side and greater than the element at the right side. So this is what makes it a Bytonic peak. So basically what we do is we apply a binary search algorithm on this mountain. If the element is, if this element, take for example 3, is greater than the element before it but less than the element after it, then we make L is equal to m plus 1. So I'm telling, okay, it's not on this side of the peak, search on the other side, on the right side. However, if the element is, in this case, element is greater than the element after it but less than the element before it, so it lies on the right side of the peak. So what I do, U is equal to m minus 1. So this is our basic intuition for this problem. Let's quickly code it out. L is equal to 0, U is equal to n minus 1, while L less than equal to U, M is equal to L plus U minus L by 2. Now, there is a certain case where if we touch any of these elements, right, 1 and 2, I mean, 1 and the starting element or the ending element of this, there is no element on the, for the starting element, there's no element before it for it to compare, and for the ending element, there's no element after it for it to compare. So in these two cases, if you're using some languages, I mean, any language will throw an array index out of bounds exception, right? So in order to solve this, whenever we reach this point where only L and U are the same, we just print that element as a Bytonic peak. Oh, I'll just write it down for you to understand. If L is equal to U, then it's one of the cases where it is a Bytonic peak. Then obviously the other case for the Bytonic peak where it is greater than the element before it and greater than the element after it. So that condition to be right, or ARR of m greater than ARR of m minus 1 and ARR of greater than equal to, because plateaus are allowed to, and ARR of m greater than equal to ARR of m plus 1. So in this case we just return ARR of m. Now elif ARR of m less than ARR of m plus 1. So basically what this means is this element lies on the left side of the peak. So L is equal to m plus 1, else U is equal to m minus 1. So let's just look at it. If ARR of m is less than ARR of m plus 1, it lies on the left side of the peak. So basically what we're telling is good search, increase L to m plus 1 and then search. If it the other condition is ARR of m is greater than ARR of m plus 1, so that means you have to search on the other side of the peak. So let's just run this code now. Perfect. So that is our solution to the problem. Now let's quickly move on to the next problem. So the next problem we'll be taking up today is the coin change problem, right? So let us quickly look at the coin change problem. So basically what it's saying is, given an integer array coins of size n representing different denominations of currency and an integer sum, find the number of ways you can make the sum by using different combinations from coins. Assume that you have an infinite supply of each coin and you can use any coin as many times as you want. Okay, so this I think is fairly easy for us to understand. So basically they are asking us here, find the number of ways you can make the sum for by only using these coins, right? So let's just try that out. how many ways we can, and they're saying the output needed for them is 4, right? So let me just try how that works for 4. So you can either make 4 by using 1 comma 1 comma 1 comma 1. That's one possibility. Or because 1 plus 1 plus 1 plus 1 gives us 4. One other combination we can use here is 1 comma 1 comma 2, which also gives us 4, or just 2 comma 2, or finally 1 comma 3. So the number of ways you can make 4 is 4 using these three coins, 1, 2, and 3, right? So in order to solve this problem, so what we'll technically be using is some dynamic programming approach, right? Because otherwise it's far too hard or far too complex in terms of time to solve this problem. Because if you're trying to generate all the possibilities of how many ones you can generate, or how many twos you can generate, how many threes you can generate, then it becomes the time constraint becomes exponential, and probably you're not going to get the answer forever, right? So we're going to use some approach called dynamic programming. So let me just so first what I'll do is the sum that I need is 4, right? So 0, 1, 2, 3, and 4. Right? So I think this was not needed. Right? And the coins that we have is 1, 2, and 3. Right? So can okay, let me just erase this. Doesn't look great. Okay, so these are the coins that we have. So first what we'll do is we'll initialize this list from value 0 to 4. That is a list of sum plus 1, right? So sum plus 1. So that those are the number of boxes in the list, and everything is initialized to 0 at the start. Okay, except dp of 0. That means the so let's just call this list dp, right? Because it stands for dynamic programming, makes it easy for us to remember. So dp of 0 is 1, except that all other elements are 0, right? So first we consider in the coin 1, right? Let's consider we just have the coin 1, and we're going to find in how many ways we can make these elements. So the basic logic behind this would be something like, just give me a minute, for coin in coins, for j in range, coin comma sum plus 1. And then finally we have dp of j is plus equal to dp of j minus coins. So let me just increase the size. So this is our basic understanding of this problem. This is the whole crux of the whole problem. So let me just um, demonstrate it for you. Okay, so for coin in coin, so this is basically our coins list, right? So we have 1, 2, and 3 as our coins. So for coin in coin, for j in range, coin, comma, sum plus n. So basically we're telling iterate through the whole DP list from starting from the value of the coin. And then dp of j plus equal to dp of j minus coin. So what does that mean? So let me just dry run through with the when coin value is 1. So for j in range, coin comma sum plus 1. So the values that in the first iteration it can take is 1, 2, 3, 4, 1, 2, 3, and 4, right? So these are the values that j can take. So dp of j, so dp of 1 plus equal to dp of j minus coin. So basically just coin value is 1 in the first iteration. So uh, dp of 1 is equal to dp of 1 minus 1. So dp of 0. So 1. And same thing for 2. This will take just the previous value. 3. This will take the previous value. 4. This will again take the previous value. So basically, what does this mean in terms of the problem itself? So basically, what they're saying is when you have one coin, you can make the value 1 by just taking this 1. So in order to make 2, we can make 1 comma 1. So whatever we had for to make 1, we just add one more value 1 coin to it, and by 1 comma 1 we can make 2. The same logic applies for 3. Whatever we had for the coin value of 2, how many other ways we could make 2 by, by just adding one more of this coin, that is coin value 1, we can make 3. So 1, comma 1, comma 1. Then for 4, it's the same logic, right? So 1, comma 1, comma 1. We could make 3 by using 1, comma 1, comma 1. And now when we add the value of coin 1, we get this. So 1, comma 1, comma 1, comma 1, right? So every single number here we can make by uh, in one way, right? By using the coin 1. Now let me take the case for go to the next iteration where coin value is 2, right? So in this iteration for coin and coins for j in range, so j will take up the values 2, comma 3, comma 4, right? So now let me apply the same logic to when I'm taking the value 2. So again, it starts from dp of 2 is equal to dp of j minus 2. So dp of dp of 2 is equal to dp of 2 minus coin value in the second iteration is 2, right? So dp of j plus equal to dp of j minus coin, right? So from 0, by adding this coin 2, I can come to 2. So basically what this means, simply take the coin 2 itself, right? Now, going to 3, dp of 3 is equal to dp of 3 minus 2. So, from 1, I can get to 3 by adding the value 2. So, I can either make 3 by 1, comma 1, comma 1, or from 1, I can directly jump to 3 using 1, comma 2. Alright, so these things will also be updated. And the same thing, but for 4, if you see, 4 can be made in either 1, comma 1, comma 1, comma 1, or by adding 2 to the number of ways I could make 2 by. So it can be, if you see, let me take the first one. I can make 4 by 1, comma 1, comma 1, comma 1, or 1, comma 1, comma 2. Or take this 2 and make it 2, comma 2. So the total number of ways I can make 4 would be 1 plus the value at dp of 2, that become 3. So this is the basic intuition of solving this problem. So let's just quickly code it out, right? So first what we do is first have a list of just ones. First make a list called dp, initialize it to all 0 values. Just set the value at 0 to 1. Now for coin, in coins, for j in range, coin, comma, sum plus 1, right? We're just going to write the same logic that we wrote before. dp of j plus equal to dp of j minus coin. And then we're going to return dp of sum. It's the last element, right? So, which is the element that we're trying to get. So let me just run this. Sorry about that. This has to go in brackets. Yes. Perfect. So now we have solved this problem to the coin change problem. So basically, what the coin change problem was is trying to find how many ways we can make a given sum uh, given a number of coins with certain values. And also remember, we can use each of these coins as many times as we want. So, and if you have to take one thing away from this problem, is that this problem takes some sort of a dynamic programming approach. If you do it by any other exhaustive search methods, probably you will not be able to solve it within the given time constraints. Okay. So now let's just quickly move into BFS, right? So now we have come to a very, very important part in our algorithmic series where we're going to understand algorithms that will help us not only solving these two questions, but may help us solving in almost any sorts of graph problems in the future, right? So BFS and DFS are very, very crucial algorithms and they have applications in many fields. For example, AI or just searching uh, allocation problems. So anything that you can think of, maybe you can model as a BFS or a DFS problem, right? So let's just quickly go to those two problems, BFS of a graph and DFS of a graph. Okay, now the question, what is breadth first search and what is depth first search? Okay, so before we even start going to the problem, we have to build an understanding of what we are trying to solve, right? So let me just draw out. Okay, sorry about that. Whenever we find a question, our first approach should be to read the question, right? So let me do that. Given a directed graph, the task is to do breadth first traversal of this graph starting from 0. One can move from node U to V only if there's an edge from U to V. Find the BFS traversal of the graph starting from the zeroth vertex from left to right according to this input graph. Also, you should only take nodes directly or indirectly connected to node from node 0 in consideration. Okay, if you're encountering BFS for this for the first time, probably you don't understand what all of that meant. So let me just draw this graph for us to get on a common page, right? So 0, 1, 2, 3, and 4, right? So this is how our graph looks. Okay. So now how are we going to solve this problem? So let me just draw the whole thing again. 0, 1, 2, 3, and 4. Right. So basically what breadth first search is, it's usually a search algorithm in trees and graphs and things like that, right? So what is breadth first search is when, let's say you're trying to search for an element called 4, right? There, in a human understandable way, we can just look at this graph and say, hey, buddy, 4 is here. But in data structures, when they are stored, for example, a node inside the graph only has knowledge of itself and the closest neighbors to it, right? It does not have knowledge of the whole graph where each of these elements are stored. So that is why a search algorithm is implemented, right? You really can't, if you're starting from a particular node and if the value that you're searching for is not that node, you really can't directly jump to where that location of that node is and return the result. You really have to traverse through the whole graph and find the node that you're looking for. So there are two approaches, right? So you can either start from this central node where you are currently and search all, like let's say you're in a building, right? And you are trying to find some book kept somewhere in some drawer. Okay, one thing that you can do is okay, a better example would be this itself. Let's not diverge from the topic and get confused. So in the let's say you're standing at this point 0 and all these and you're trying to search for the room number 4, which is you're trying to search for the number 4, right? So one approach that you can take is either first visit the place 1, and then if any place is connected to place 1, for example 5, 6, and so on and so forth, you can first visit the place 1 and you can go to the immediately connected place 5, then 6, then 7, and search like that. So you go depth by depth by depth. So you're just traversing. First you traverse one node you can, and from that node you traverse it to connect node connected to that node, and so on and so forth, right? So you are going somewhere in like this depth first fashion. Another way you can another search approach that you can take is just search all the neighboring nodes. For example, if you take 0, right, in order to search for 4, first instead of going to this node and going to 1 and then going to node connected to 1, you search all the neighboring nodes of 0, right? First you go this level, 1, 2, 3. Once you have searched this level, then you go to the second level. So basically you're searching, exhaustively searching all the neighbors of the current node, and when you're not able to find it, then you go to the next node and then search all the neighbors of that node, and so on and so forth, level by level by level by level, right? Depth is different. So let me just show you how BFS and DFS will work on this graph. So if I'm applying BFS on this graph, right? BFS is applied through a data structure we can say called a queue, right? So queue is basically uh, first in first out data structure, right? So if you're going to buy a ticket in the movie theater, you go first in line. So you are going to get the queue first, right? Uh, there's another a data structure called stack. Basically, that is first and last out data structure or a last and first out. For example, let's say you are making some chapatis for dinner, right? And you go make it at the stove and put it on a plate. So if you think about it, the most recently made chapati will go on the top, right? And when you're going to eat, you're going to get the hottest chapati, the one that was made the most recently, right? So that is a first in, last out data structure, a last in, first out data structure. So BFS is implemented using a data structure called a queue. So now let's just do the BFS on this graph. So basically, let me just have this queue and let me have this result, uh, this thing as well, result array as well. So first, we just write our source node inside our queue. First, what we do in BFS is, and as long as the queue is not empty, what we do is pop the first element out of the queue, right? Pop the first element out of the queue and load all its neighbors inside the queue. So how this will work? So 0, 1, 2, 3. I'm loading all the neighbors inside the queue, 1, 2, and 3. And as soon as you pop out the element, put that in the result, right? So we put 0 into the result and then put 1, 2, and 3 inside the queue, right? After this, what we do is, once I put 1, 2, and 3 inside the queue, then I pop the second element. I pop the second element, put that in the queue, and then I check if this element 1 has any neighbors. No, right? So it does not have any neighbors, so we don't have to add anything to the queue. Then we pop 2. Once we pop 2, we immediately find it has a neighbor, 4, and we put that in the queue, and we put 2 in the result. Same thing for 3. We visit 3, put that in the result, and we try to find if it has any neighbors. No, so we don't have to add anything to the queue. Finally, we pop 4. We put that in the list, and does 4 have any neighbors? No. And now if you see, the queue has become empty. So once the queue becomes empty, we stop. This is where our breadth first traversal ends. So let's just look at how the BFS would also work for this graph before we continue. 0, 1, 3, and 4. Now, as I said, DFS works on this data structure called a stack, which is quite different from our BFS implementation. So let me just write DFS here and let me stack. Okay, and this is result. Okay, so uh, I'll just change this up a bit for us to actually understand. DFS can work in two ways, right? You can either from 0 to 1, you can go and visit all the nodes of 1, or your first node can be 0 to 3, you visit, and then you do the depth-wise search of 3, and then depth-wise search of 2, and depth-wise search of 1. You can go from right to left or left to right. So let's just look at uh, how to make this a left to right search, right? Because if you're using a stack and reading the data structure from left to right, and it reverses inside the stack. So we don't want that situation. We'll just make a slight change to our algorithm, right? So first, in our stack, at the starting stage, we just have this value 0, right? So again, it's very, very, very similar to what we did earlier. The approach is the same. First, eliminate, I mean, pop out the element from the stack. So when you're popping out from the stack and there's only one element, obviously 0 gets popped out. Add that to the result and add all the neighboring nodes of 0 into the stack. So this is where we're going to make a slight change. Instead of adding it as 1, 2, 3 inside the stack, we'll add it in the reverse direction from right to left. So 3, 2, and 1, right? So this is our current stack status. Now again, now when we pop from the stack, which element gets popped? 3. I mean 1, right? Because that is the topmost element of the stack. So once I pop 1, I add it here. Does 1 have any neighbors? No. So I continue as is. Now then I pop the next element, 2. Yes, so 2. And does 2 have any neighbors? Absolutely it does. 4. And then I continue. Now what I do is, when I pop the element in the stack, I get 4. Now, does 4 have any neighbors? No. Then I get finally the only remaining element is 3. Then I pop that and write 3. And now the stack is empty. We stop our depth first traversal. So this is basically how these two algorithms work. So let's just quickly code out these two algorithms and solve them. So in depth first search, we are okay. So here, though in Python we can probably, when the problem is very very simple, we can just do it using a list data structure itself. But because we have talked about the implementation using queues, let me use the queue data structure, right? So result will basically store our resultant list. That means what we get after we have traversed all these nodes. So queue is equal to queue and empty queue. So initially what we put inside the queue, that is a zeroth element, right? And then what we do is we should also have one more set called visited. This is basically for a simple reason. Like let's say we have this sort of a graph, right? Um, where for some reason like more than one nodes are connected to another node. For example, 1 and 2 are both connected to 4. So the idea is that once we have already visited 4 through this 0, 1, 4 path, we should not ideally come back and visit node 4 because from 0, 2 and 4, 0 to 4 path, right? Because we've already searched 4. We don't have to go back and search 4 through another path. So that is why we maintain this visited set. Okay. Why q not q dot empty, right? So basically, when do we do this BFS algorithm for? As long as the queue is not empty, right? So then what we do is u is equal to q dot get. If you remember our previous notations from our first session, when we say u, we are talking about the current node, and when we are saying v, we are talking about the neighboring nodes of the current node. If not u in visited, okay, so then we did res dot append u visited dot add u, right? For v in adjacency of u. So for all the neighbors of u, so basically you do q dot put v. Finally, what we do? Return res, right? So let's just run this as well. Okay, perfect. Now we have done BFS. Now let's quickly move on and go to DFS, right? And just to show you how similar both these algorithms are, BFS and DFS, I'm going to take the exact same code from here and apply it for our DFS problem, right? So let me just remove this, go to our DFS problem. Let me just paste it here, right? So this will remain as is. Res is equal to empty linked list. I mean empty list. One thing that will change here is we'll have this new data structure called stack. Stack is basically implemented using just a list. We're not applying any new special data structure here. And here what I do is while len of stack greater than 0, okay, u is equal to stack.pop, okay. If not u in visited, res dot append u, visited dot add u, while v in for v in reversed. Okay, now why do I do reversed adjacency of u? This is basically for the problem that we saw, right? When we are trying to do left to right, we have to in our output, they are asking for us to do left to right search according to the graph. But when we start putting elements in the graph from left to right, and then we pop them out, the elements in the stack from left to right, and then we pop them out, we get them in the right to left fashion, right? They get reversed. So in order to do that, so while pushing elements inside the list itself, we reverse them. So that's why this reversed is very essential for us. And then basically what we do is stack dot append v. Okay, and let me just run this. Mhm. Oh, okay. So this is a very, very silly thing that I have done. So if you remember, uh, when I saw this graph, I told you that we do this algorithm as long as the stack or queue are not empty. But if you look at our code, I haven't given any starting node to the stack. So what it's basically saying, hey boss, you don't have any node in your graph, so I don't have to search. Good for me. So it doesn't give us any result. So let me just put our first element into the stack. And we run the code. The internet is a bit slower than usual today, so we're facing some difficulties. Perfect. So now we have also solved our DFS problem, right? So now the problems left for us are insert a node in a BSD, rotate by 90 degree, summed matrix, and finally Dijkstra's algorithm. Okay. So after this stream, I probably advise you to go back and look at BFS and DFS problems because, as I said from the start, they are very, very crucial algorithms. And once if you understand BFS and DFS, I'm pretty sure you will be able to solve most of the graph problems. Because if you don't understand these two algorithms, you're probably never going to have that motivation to solve harder graph problems, right? So, but once you understand them, I feel graph problems become so much easier to traverse and do, right? So let's learn BFS and DFS properly. Finally, now let's move on to the next problem, which is also a crucial problem in our understanding of trees, right? It's called insert a node in a BST. So what they're saying is, given a BST and a key k, if key is not present in the BST, insert a new node with a value equal to k into the BST. If k is already present in the BST, don't modify the BST. So just for our reference, what a binary search tree is a tree with where each node has two children and the left child is always smaller than in some cases you can if the BST has duplicates you can even usually we don't have duplicates in BST, right? But sometimes if you can even have less than equal to or greater than equal to, but we don't call them they're not used generally. So just for our definition, we'll say a BST is a tree in which where the left node is always less than the parent node and the right node is always greater than the parent node, right? So that's our BST. Left is always smaller, right is always greater, and we have our parent. And also every single node is a in itself a BST or every subtree is also a BST, right? So these are our two crucial points: left smaller, right greater, and every single node is also a BST, right? So that is our binary search tree. So what they're asking us to do here is insert a node into a binary search tree. If the node is already present, don't insert it, just return the tree as is. If it isn't present, insert it into the correct location and then uh, return, right? So here what we have is 2, 1, 3, and our node to insert is 4, right? So here what we do is whenever we have to insert a node into a binary search tree, first we have to find the correct location where to insert it, right? So how do we find the correct location where 4 must go? First, our root is first here, right? First, compare the value at root to the key. So the key is 4, root is 2. Is key greater than 2? Yes. So ideally, where should the key go now? Should it go on the right side or the left side? Remember, right side will always hold greater valued elements and left side will always hold smaller valued elements. Now, because 4 is greater than the root, I should start searching for the on the right side of the tree. So now I shift R to here, root to here, 3. Now again we look at 3. Now if is 4 greater than 3? Absolutely it is. So then we start searching in this empty space, right? Now one thing that we do here is once we reach an empty space, we basically find that the node that we were looking to insert was not present in the tree. So what we basically do something very simple. We just place 4 there and return the actual root of the tree. And what happens if I was trying to, instead of trying to insert 4, I was trying to insert 3. All right. So again, we compare 3 with 2. 3 is greater than 2. So we come to this location and we find 3 is equal to the value 3 is key 3 is equal to the root 3. So that time without modifying the tree, we just send the tree back as is. So how do we write this in terms of code? As we discussed earlier, if we reach any empty location in the tree, that means what that basically means is that uh, key was not present in the tree. We have to add it. So return node of key elif root dot So if key is greater than root dot data, on which side of the tree we have to insert our node? On the right side. So we do root dot right is equal to self dot insert root dot right and key. Elif key is less than root dot data, root dot uh, left is equal to self dot insert root dot left key. And the only other possibility is that we have the only way we reach the final end is either we have put the nodes the key node in the correct position, and then we reach the root of the tree and then ready to send it back, or the root is already present. I mean, the key is already present in the tree. So that we just without any modification, we just send root back. So let me just run this. Okay, perfect. So our insert into a BST is also completed. Insert a node into BST, right? So now let's look at another problem, which again is quite essential to our understanding of matrices as well. So let me just go to it. It says rotate a matrix by 90 degree. So let me quickly find that problem wherever it is. Yes, here it is. Rotate a matrix by 90 degree. So given a square matrix of n into n, the task is to rotate it by 90 degrees in anti-clockwise direction without using any extra space, right? So if we just think about a clock, basically what they're saying is 1, 2, 3, 4, 5, 6, 7, 8, 9. If you rotate this in an anti-clockwise direction, right? So the 3, 6, 9 will go on top. Then we'll have 2, 5, 8. Then we'll have 1, 4, 7. Okay, so that is basically our anti-clockwise rotation. So just imagine each row just getting rotated by 90 degrees, right, to the left. So this is what happens. Now, this may be seem like a very simple problem, right? Just initialize a new matrix, use some sort of smart indexing for your old array, and then just shift all these elements into the new matrix, right? It's quite simple. But here is where their constraint comes into play. I'm sorry if not able to look at this matrix because of my camera. So this is what a anti-clockwise 90-degree rotation would look like, right? So now, but they have given an extra constraint. The task is to rotate it by 90 degrees in anti-clockwise direction without using any extra space. So this makes our problem a bit more tricky. We can't initialize a new matrix, can't load all these elements into the new matrix and return it. We have to modify the old matrix, right? So how can we go about doing that? Okay, so let me just write this. This is our input array 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now in order to rotate, to bring this 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9 to 3, 6, 9, 2, 5, 8, 1, 4, 7. How do we do this without using any extra space? So this is quite tricky, right? This problem. One basic two-word solution for this problem would be transpose, transpose, or two-phrase solution rather, transpose and reverse column. So one is transpose and two is reverse column. So let me just apply these two logic here. So in when I transpose this, basically what I get is 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? This is our transpose step. right? So that is our transpose step. And now let me just do the reverse each column. So I reverse each of these columns, right? So how do I do that? So I get 3, 2, 1, 6, 5, 4, and 9, 8, 7. So is this our required output? 3, 6, 9, 2, 5, 8. So is this required output? Absolutely, right? As you can see here, 36369, 258, and 147. So 369, 258, and 147. So again, the two-word solution for this, I mean, two-phrase solution for this problem is transpose the whole matrix and then reverse each column. So let me just quickly code that out as well. So this will be our transpose step for I in range n, right? For j in range I. So this is our transpose step. So I of I j, a of j I is equal to a of j I, comma, a of I j. So that is our transpose step, and this is reverse each column, right? This reverse each column step. So for I in range n. So basically in this step, what I is doing is it will point to each column, and then we'll be reversing each column through the following process. For j in range n by 2, a r a of j comma I comma a of n minus 1 minus j is equal to a of n minus 1 minus j a of I comma a of j comma I. So return. Do we have to return anything? You have to modify it. Okay, I think we don't have to return anything in this problem. So let's just run it. Ah, yeah, bad. Yeah. So basically what we've done is we have transposed the matrix and reverse each column. So just to give you some intuition of this, a of j comma n minus 1 minus j. So what will, so let me just run that on this new matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I will be going through each of these columns. So 0, 1, 2, right? So this will be our I values. And j will basically go from, in each step it will go to 0 by 0 to n by 2. So the value of n here is 3. So 3 by 2 is 1. So basically j will take the values from 0 in each of these columns. For example, so let's just look at this situation. For the first step, I will be equal to 0 and j will be equal to 0. And n minus 1 minus j. So what is n minus 1 minus j? N minus 1 basically denotes the last um, row value, right? So if row value is the number of rows in the matrix are 3, then the index of the last row will basically be 2, right? N minus 1, 2. So that's what basically n minus 1 is denoting. So I'm basically telling swap this value uh, j with n minus 1 minus j, right? So n minus 1 minus j is 2 in our scenario, right? So when I swap these two, what do I get? 7 will go here and 1 will come here. So basically this is reversing each of these columns. So that's all that step is doing. So again, just to go through the solution to rotating a matrix anti-clockwise by 90 degrees, given that everything has to be done in place and you cannot use an extra matrix, is basically first you transpose it and then reverse each column. So that is the intuition behind this problem. So let me just perfect. So now we have solved this problem too. Let me quickly go and solve the next problem of the day. That is our summed matrix. Okay, so a matrix is constructed of size n into n such that m of ij is equal to I plus j. Count the number of cells having the value q. So basically, what they're saying is we have, if n is 4, basically you have this matrix, a 4 into 4 matrix, and they're telling to find how many value or times this value q equals 7 appears on inside our matrix. So how are the values inside of the matrix denoted? Let me just show that as well. So because n value is 4, so this is 1, 2, 3. Wait, let me just write that in a different color sketch pen. So this n value is 4, 1, 2, 3, 4, 1, 2, 3, 4, right? So, right. So, okay, let me just take a black pen and come, right? So, the first value is just basically 1 plus 1, that is 2, then 1 plus 2, 3, 1 plus 3, 4, 1 plus 4, 5, then 2 plus 1 is 3, 4, 5, 6. Then 3 plus 1 is 4, 5, 3 plus 2 is 5, 3 plus 3 is 6, 3 plus 4 is 7, and 4 plus 1 is 5, 6, 7, 8. So this is basically how the matrix values are represented. Now if Q is equal to 7, what is the number of times 7 appears in this array? 2 times, right? 7 and 7. So that is basically the intuition of this, understanding of this problem. So the values inside an array are decided by the sum of their row value and the column value on one based indexing, right? So the first value is 1 plus 1 is 2, and the last value is basically n plus n, right? So that is the basic intuition of this problem. Now let me just code out the solution. Now, what sort of values will not appear inside our result? So any value that is less than 2 will not appear inside our result, inside our matrix, and any value that is greater than n into 2 will not appear inside our matrix. So how do I return that? If q is less than 2 or q greater than 2 into n, return 0, right? Now what about the values inside our matrix? So the value exists inside the matrix, but how do I find how many times that value appears inside the matrix, right? So let us just look at the middle column, right? The diagonal. The diagonal appears for the most amount of times. So the value of a diagonal is basically n plus 1. And how many times is the value of the diagonal is actually n plus 1, and how many times the values inside the diagonal appear? For n times, right? So if the value of q is equal to n plus 1, so value of q was actually 5. 5 will appear how many times? N times, right? So 1, 2, 3, 4, which is equal to n, right? But now if you look at some other element, let's look at 7. What is the difference between the value 7 and the value at n plus 1? N plus 1 is 5, and the value 7 is just 2 times greater than uh, the value 7 is 2 times greater than the n plus 1. So let me just, for understanding, let me call this optimal value, right? Optimal. So 5 is our optimal value inside this matrix, and our q value is 7. And optimal value occurs how many times? N times, right? So n times is equal to 4. Now, the distance between our optimal value and uh, our new q value will be the same amount of the distance between the number of times the optimal value occurs and the number of time q value occurs. Just to make it very simple, so if our element 5, let me call this val, and let me call this occurrence, number of times it appears. The element 5 appears 4 times. The element 6, 7, 4, 3, 2, right? The element 6 is 1 away from element 5. So element 6 will appear how many times? 3. Element 4 is 1 away from our optimal value, 4. So how many times element 4 will appear? 4 minus 1, that is 3. 2, 1, 2, 1. So this is the basic understanding of this problem. So as much distant as the new q value is from the optimal value, that many times less it will appear inside the matrix. So before we get confused, let's just code out the solution for better understanding. So return. So what is the number of times the optimal value appears? N minus n plus 1 minus q. So what is n plus 1? This is our optimal value and this is new value, right? So ABS. So based on the absolute distance of the new value from our optimal value, those many times number of occurrences will decrease from the optimum. So let me just write this down. Okay, let me just run it. Okay, there is also a one-line solution for this. We can just optimize our code to remove this and say max of 0, comma. Okay, so this is obviously the case when we have such a distant value from we have such a distant value from the optimal value that it does not occur at all in the matrix. So that time we just return 0 because we'll get n minus abs of n plus 1 minus q, we'll get as a negative value. So instead of that, we just return 0. Else we just return n minus 1, n minus abs of n plus 1 minus q. So that is the basic understanding of this problem. So finally, let's go to our final problem of the day, which is the Dijkstra's algorithm. Okay, so just to before we even get into Dijkstra's algorithm, we have to basically understand what Dijkstra's algorithm is. Why is it so useful in almost any sort of sector that we can think of, right? So basically, Dijkstra's algorithm, if you are not aware of graphs or something like that before, s- basically a Dijkstra's algorithm is a shortest path routing algorithm, right? So it's a single source shortest path routing algorithm. For example, I am at my home now, and there are many malls nearby. There's my college nearby, and there are many sorts of playgrounds nearby. So ideally, if let's say I want to go to the playground, when I go to the playground, I wouldn't be taking the longest route to the playground, right? Because I want to get to the playground as fast as possible. So in my head, I would have gone to the playground a couple of times, but immediately I would have found, okay, what is the shortest route going from my home to the playground, and I'll take that route and go to the ground. And same thing for college, I'll always take the shortest route to college. Same thing for the mall as well. I'll always take the shortest route to the mall. So if you think the source is always the same, right? That is the location of my house. And the idea is that I always take the shortest path from the single source that is my house to all the other nodes or the destination points, right? Now, it's quite obvious, right? Where would Dijkstra's algorithm find the most application? Basically in any sort of routing applications, for example your Google Maps, right? So Google Maps would use some sort of implementation of Dijkstra's algorithm to tell, okay buddy, this is the shortest distance to take from your source to the destination that you want to go to. And even this is used in networking, right? So when you're sending messages over the internet, you would want your messages from your source computer to go to any other computer as fast as possible. So this is crucial because again, as people are sending more and more messages over the internet, we have to optimize for time, right? We have to send uh, the message as fast as possible. So that is again Dijkstra's algorithm where we optimize by the time, the shortest path. So these are the things we can, and usually Dijkstra's algorithm, we either in real world applications is usually done by time or the distance. So we are trying to optimize in terms of distance or optimize in terms of time. So that is the basic um, idea of what Dijkstra's algorithm might be. So now let's just look at a diagrammatic representation, right? So let me say this is my home. Okay, that's my home, and this is some sort of a hospital, and this is some sort of a bus stop, right? So this is a bus stop, okay, and this is a mall. All right, so that's my home. This is a hospital. This is a bus stop, and this is a mall, right? So in, initially, all these places are considered to be at infinite distance away from my house. So, and let me say from my house to the bus stop, it's taking, let's say, just, I mean, house to the hospital, it's taking 2 minutes. And from the hospital to the mall, it takes me, let's say, 20 minutes. All right. But from my house to the bus stop, it takes, let's say, 3 minutes. And from the bus stop to the mall, it takes barely like 1 minute. Okay. Because the bus is pretty fast. Now I have to decide if I'm going to the mall, in what sort of path should I take? Should I either walk to the hospital and then walk again to the mall, or should I walk to the bus stop and then go to the mall through a bus? Okay. So now let's just apply Dijkstra's algorithm. Whenever you're applying the Dijkstra's algorithm, the location at we start out at, the distance is considered to be zero. And the location of all the other points inside the graph is considered to be at infinity, right? So all the other points are set to be at infinite distance from where I start. Okay. The core concept of Dijkstra's algorithm is a step called relaxation. Relaxation you would find in many other routing algorithms. So let's just look at what a relaxation might be. So I'll just tell you the steps that we take to implement Dijkstra's. When you start out, always start at the closest unvisited node. For example, now none of these nodes are unvisited. So which is the closest unvisited node? Basically our home itself. So that is zero. And now try relaxing the paths to all the neighbors. Okay. So what does relaxation mean? First, I assume that the hospital was at infinite distance from my house. But once I visit my house, I'm at my house, and I know that from my house, so that is, let's say our house was U and the hospital was V, right? So I know D of U is equal to 0, D of V is equal to infinity, and the cost. So cost of cu comma v. The cost basically means the path cost, right? So the path cost is the amount of time it takes on that particular path. So the amount of time that it takes in this particular path is 2, right? So the c of u comma v is 2. So now let me apply relaxation. So basically what relaxation says is d of v is equal to min of d of v comma d of u plus C of UV. Okay, what does that essentially mean? So our d of v is initially at infinity. Now, if I find a better way to get to my v, then I would say, okay, the best way is not what I assume currently, but it is that better way that I uh, got to come here. For example, from my house, I know my house is at a distance of 0, and from my house, I know the bus hospital is at a distance of 2. So distance of home plus the cost of the path, 0 plus 2 is 2, is, and 2 is less than infinity. So now I know that my shortest path to the hospital is 2, right? I mean, the distance of the hospital from my house is 2, which is less than infinity. So now when somebody asks me, hey, how much time do you think we'll get to the hospital? I will not say, oh, it's at infinity, and I don't think how I know how to get to the hospital, but I'll rather say, oh yeah, it takes me, the hospital is at 2 minutes distance away from my house. The same logic I apply for the bus stop. So 0 plus 3 is less than infinity. So now this gets changed to 3. Now again, let me we have visited all the neighbors of our house. So now we go to the next step. Visit the minimum unvisited neighbor. So which is our unvisited neighbor or minimum distant unvisited neighbor so far? The mall is at infinite distance. I cannot visit it. Yeah, bus stop is at a distance of 3. May be possible to visit, but our hospital is only at a distance of 2. So what we do? We go and visit our hospital. Now our hospital is also visited. Okay. Now, what are the neighbors of the hospital? The mall is a neighbor of the hospital, right? So again, we perform relaxation. Distance of now the u becomes 2, v becomes d of u becomes 2, d of v becomes infinity, and the cost becomes 20. So 2 plus 20, 22 is again much less than infinity. So we update this to 22. So that means there is a path that can take me in 22 minutes to the mall. Which is that path? going from my house to the hospital and then from the hospital to the mall. So that takes me 22 minutes. Now again, we do the same step. As long as all the nodes are unvisited, again we visit the minimum unvisited node. The minimum unvisited node here is our bus stop, right? I visit the bus stop. Now, I see, look at the neighbors of the bus stop. The mall is a neighbor of the bus stop. So D of U here is 3, D of V is 22, and C of U comma V, that means the cost of this path is 1. So now 3 plus 1 is 4. Is it less than the current path cost? I mean, current distance of the mall? Absolutely. 3 plus 1 is 4. 4 is less than 22. So we relax. So I cancel this and make this 4. Right? Now we have visited this path too. Finally, we just visit the mall too. Now what? Now we come to a base question. What is the shortest time I can get to the mall? 4 minutes, right? And which path should I take? First, I should go to the bus stop, then take the bus and go to the mall. And I can do the whole thing in 4 minutes. So this is a basic understanding of Dijkstra's algorithm. Um, and now that we have just seen a few nodes here, you may think, okay, wait, this is not that, maybe it's not that highly useful, but Dijkstra's algorithm can also be applied on a node of like 10,000 node graph, right? And it can give you the shortest paths in to all these locations from a single source. So that is why Dijkstra's algorithm is very essential and is almost used in any computer science algorithm that you can think of, right? So now let's just quickly code it out. So basically, what going to do is for our infinity assumption, I'm just going to initialize a variable called inf. And now let me first initially set all the nodes at infinite distance. Okay. And then a distance of, I'm not sure if this will be visible with my camera too, but so let me just pull that to the side. So distance of source is equal to 0 because when we're starting out at some point, obviously where we are, the distance to that where we are is 0, right? So visited. So this will basically tell us if a certain node has been visited or not. So initially all the nodes are unvisited. Now for I in range, we do the following. Now U is equal to get min unvisited node. Okay, I'm going to supply these two things, uh, visitor and distance. Okay, so basically at what we do at each step, we find the minimum node, that minimum distant node that has still been unvisited, and that becomes our current node, right? Or the node to visit. So once we visit that node, what do you do? Visited U is equal to true. Now, for if we just look at the example, right? So basically all these like adjacency list values, they are given as a pairs of two values. So the first one detects to which neighbor the current node is connected to. So u, if it is 0, it is connected to 1, and the next value gives us the cost. So 0 is connected to 1, 0 is connected to 1 with the cost of 9. So for v comma c in adj of u, okay, so for basically find all the neighbors and the corresponding costs that are connected to the current node. Okay, so again, if you look at our previous session, we just told this is a convention when we write algorithms for graphs, especially we say u is the current node and v is the neighboring node, right? So v comma c in adj of u, distance of v is equal to min of distance of v comma distance of u plus c. So this is our very famed relaxation step. Relaxation step. So then finally, we just say return of list. Now we have to define one more function. If you remember, we say this get min unvisited node. This function we just have to define. So before that, I'll just call it like this, self def get min unvisited node. So this will take visited and distance. Min node is equal to -1, min dist is equal to 1, 0, 0, 0, 0, 0. Okay, for I in range len of visited, if not vis if not visited of I, and distance of I less than min dist is equal to distance of I, and min node is equal to I, and then basically just return, sorry, min node, right? So what we're basically saying is initialize a constant 1000, like a million, just to denote a very, very high value. Assume that all the nodes are initially at infinite distance, set the distance of source node to 0 because that's where we are at. And then also initially all the nodes are unvisited, right? Now try for every node present in the array, you have to perform this algorithm. So you will be our get minimum unvisited node. So of all the nodes, the node that is both unvisited so far and that is the minimum distance from the source. So how does that get min unvisited node algorithm work? So it just iterates through all these nodes, and if that node is not yet visited and it the distance is uh, lesser than the current than the minimum distance so far, it takes that as our new min node, right? So then we return that minimum node. Now for all the neighbors of you, and so for all the neighbors of you, and we take v as the neighbor and c as the cost from u to that v. So we basically do a relaxation step. So d of v is equal to min of d of v, comma d of u plus c of uv, right? So that is what we're doing. So then finally, once we've done all this, we just return our result. So let's just run this. Yes, so there you have it, guys. So that is our final question for today. That is Dijkstra's algorithm. So again, you can go back and revise what Dijkstra's algorithm is all about. And this is one of the very, very crucial algorithms that we keep using in almost any field of computer science. So that so again, just to reiterate, uh, learn all these three algorithms properly. One is Dijkstra's algorithm, one is breadth first traversal, and one is depth first traversal. So these three algorithms will help you even if you're not solving questions regularly, and they're asked almost anywhere. So all the best, guys, on your coding journey. Take care. I'll see you next week.